So today's notes are a little bit longer, but these first couple of pages I've actually already filled in everything for you. It's just serving as kind of like a review for you. So the first top here, we have a linear function drawn for you, and I put all the information that we can get off of a linear function. You can figure out its slope and its y-intercept, which actually my slope is not correct. What should my slope be? Up 1 over 1. Really, that slope should be a 1. That's a typo there. So we got an x-intercept of 0, just like we have a y-intercept of 0. It's just we call our y-intercept our b value. But really, that's our y-intercept. Domain is everything, so x is an element of the reals. Range is also everything. Y is an element of the reals. This function is 1-to-1 because it passes both the vertical line test and the horizontal line test. We talked about 1-to-1 in our last unit there. So both vertical and horizontal makes it 1-to-1. Onto means it uses all range values. So since this graph keeps going on forever, it will eventually use every single range value. So it is an onto function also. This graph is increasing. It's continuous because it's all connected in 1. And it is also an odd function because it is symmetric through the origin. So in our second graph there, that's our quadratic function. Quadratic function doesn't really have slope like we did on the last one, although this one does have a vertex at 0, 0. We got our x and y intercepts there. They're both zeros also. This is an even function because it's symmetric over the y. So symmetric over the y-axis. It's decreasing from negative infinity to 0, so we could also write that as x is less than 0 when the function is decreasing. It is increasing when x is greater than 0. And again, domain is x as an element of the reals. Range, however, is not an element of the reals. Is it ever going to be negative? No, this is never going to be below the y-axis. So our range here is actually y is greater than or equal to 0. So then we go on to our cubic. We haven't seen our cubic too much, but we do graph cubic quite frequently sometimes. So this is a continuous graph still. It flows. It's all connected as 1. This is an odd function just like your linear because it's symmetric through the origin. Symmetric through origin. Domain and range, elements of the reals. It's going to be every single number, both domains and range. X-intercept 0, y-intercept is 0. It's increasing function. Whereas our last one, our quadratic, was both increasing and decreasing. And it is also 1-to-1 and onto. It passes both vertical and horizontal line tests. Onto, it uses all of its range values possible. Take a little back. So we got our absolute value function next. Again, still continuous. It's an even function. We're symmetric over your y-axis. Domain is everything. Range is y is greater than 0 or greater than or equal to. Increasing. Again, the other way to write that would be x is greater than 0. Decreasing would be x is less than 0. X-intercept, y-intercept 0. Vertex 0, 0. And we're going to cross this out. It's not 1-to-1, it's not onto. Because this would fail horizontal line test, remember? So not 1-to-1. And it's never going to use those negative y's, so not onto. Square root function. This is another one we don't use too often, but you never know when it's going to show up. So it is still continuous. It's all one curve. Domain is greater than 0. Range is greater than or equal to 0. It's only increasing, but it is also only increasing when it's greater than 0 because that's where the graph only exists. It can't be increasing in the negatives because the graph doesn't exist there. And it does have an x and y intercept still. Now this one would be 1 to 1. It would pass both vertical and horizontal line tests. Now would it be onto though? No, because it's never going to use these negative ranges again, so not going to be onto. And then our last kind, this is our rational function, our fractions. This graph is a discontinuous graph because you have the two separate pieces to the graph there, so that's what makes it discontinuous. Range is everything except 0, because remember we have a horizontal asymptote right here at y equals 0. That's what I have written right here for you. You've also got that vertical asymptote right here at x equals 0. So your x's and your y's both can't be 0. It is 1 to 1 still. It would pass both vertical and horizontal line tests. And this is an odd function. But if you notice, it doesn't have an x-intercept, doesn't have a y-intercept, because it never actually touches those axes there. So just a little review of all of our different functions and the pieces that we've talked about them. So our main focus for today, though, is transformations of functions. So we're going to take functions and we are going to move them all around the graph. So as you can see here, I have a whole bunch of equations written up on the top here. This one is a quadratic equation because it's got the squared term in there. That's always our quadratic. A, B, and C just represent numbers, and depending on what those values are, that helps move the graph around. This next one is our absolute value. Those aren't just ones, as somebody has told me. This one is our square root. And then we got our cubic. And we got what we call our rational, our fraction one. So now transformations do need to be done in a very specific order. So you have to do certain things first, and then you do the next one. If you don't do it in the correct order, you end up with a very different function than what you're supposed to have. So first we do any horizontal shifts. So your horizontal shifts are that letter B. So if you look in each of our equations, we have a letter B. B is the value that's always right there next to x. So if there's going to be a B value, it's going to be right there next to x. It'll be x plus 1 and then squared, or like absolute value of x minus 5. It's with x. That is your B value. That's telling you to move either left or right. So next would be any reflections. So our reflections that we would have are purely over x-axis or over your y-axis. And that would just be because a negative sign. Either with A or the x. So if we take a look, A is the value in the front of every single equation. Starts with A, starts with A, starts with A, starts with A, starts with A. So if it's a negative in front of that A value, that means you're going to reflect over Y. So if it's all the way out in front, you're reflecting over your Y-axis there. All right, if the negative's all the way out in front, you're reflecting over X. I apologize. If it's with the x, you're reflecting over the y. It doesn't happen as much with the x. Generally, it's out in front, so you're doing more reflections over your x-axis than you are over your y-axis. So next you're going to do any stretches, which is also your a value, so that number out in front. So what I mean by stretches is, like, for example, if that's a 2, that means you're multiplying everything by 2, so you're going to make your graph stretch up by 2. If it's like 1/3, that means you're going to make it actually kind of stretch, quote unquote, stretch down by 1/3. So everything's coming down more. So stretching up or down. And then our last one is your vertical shift. And that's your letter C. So that's the one at the end. And that just tells us if we're moving up or down. So it follows this order, because if you notice, B is the closest one to X, so that's why we do that one first. And then A is the next closest, and C would end up being the last. So it's following that specific order because of its proximity to your variable, that letter X there. So let's take a look at some examples here. So I've already graphed for you f of x equals x squared. So we want to graph and label h of x equals x squared minus 5. Now, since this is at the very end, this minus 5 just means we're going to move down 5. So we don't even need to get a table of values. All I'm going to do is I'm going to go to the graph that I have, and I'm going to take each point and I'm going to move them down 5. Right, so I took my vertex, moved it down 5. Those next 2 points moved it down 5. Here's another point, so I'm going to move that down 5. And then that other one, I moved it down 5. So then I'm going to label that one h of x. So I took each of the points that were nice points. They lined up evenly on a box. I just simply moved them all down 5. So for j of x, I'm just going to rearrange this and put my x squared first, so it's in standard form now. So x squared plus 3. So because of the plus 3, which way are we going to move? We're going to move up 3. So now we're not going to move the one that we just drew. We're going to move the original one, that x squared one. So now I'm going to take my vertex, I'm going to go up 3. I'm going to take this point next to it, I'm going to go up 3. Up 3. And then up 3. There we go. We got j of x there. So any number at the end there tells you you're going to move up or down. So f of x plus c moves up c units. So whatever that number is, that's how many units you're going to move up. And then if you subtract it, that's going to move down, again, whatever that number is. So anything at the very, very end makes our graph move up or down. So let's practice our horizontal shifts. So now we're going to be moving left or right. And the difficult thing about the horizontal shift is it's kind of counterintuitive. It's not what you think it would end up being. Because most people in here, you see x minus 2, and you think, okay, minus, that means you're going to go to the left. But these ones are actually going to be the opposite of that. If you are subtracting, that means you're going to move to the right 2. Because the way these equations are written is it's x minus h, so it's always the opposite of whatever that value should be. So I'm going to take f of x again, but this time we're going to move over 2, and I'm going to take each of the points on that graph and move it over 2. Take this one, move it over 2. Take this one, move it over 2. And then I don't really have any other nice points that line up on that one, so I'm just going to sketch it and make my new graph look similar. There's our h of x. Everything moves over to the right 2. So then our other one on there, the x plus 4, again, it's going to be the opposite what you think because the formula is generally a subtraction. So that means you got to negate them. So plus 4 actually means you're going to move to the left 4. So 1, 2, 3, 4, 2, and 4. So again, those parentheses made the difference. If I didn't have parentheses there, and for example, this was just x cubed minus 2, then it becomes like the last problems where I just want to move my graph down 2. But because there's parentheses around it, that changes it and makes it the horizontal shift. So plus c, opposite of what you're going to think, so that means we're going to go to the left, c units again, whatever that number is. Subtraction means we're going to go to the right. And that's only true for those ones. Otherwise, up, down, exactly what you think. Plus is up, minus is down. So then the a value, again, that's a stretch or technically a shrink, but a lot of times we just call them stretches. So here, we got a 2 out in front, so that means we're going to stretch everything by 2. So that means we have to multiply the y values by 2. So if we look at our graph here, this is the point 0, 0, so 0 times 2 is 0, that's not going to change. Here I have 1, 1, so I'm going to multiply my y by 2, so that makes it the point 1, 2 now. So and this one was negative 1, 1, so that's going to become now negative 1, 2. Then over here, 2, 2, multiply it by 2, I get 2, 4. And this one's negative 2, 4. And then 3 becomes 3, 6. So you just keep multiplying it by 2. And then 4, 8. So what it's doing is it's pulling those y values up and stretching them from where they used to be. So then for j, this time we got a 1/4 in there. So we're still going to multiply y values by 1/4. So remember the other thing you could do, instead of multiplying by 1/4, what could you do? Divide by 4 is the other way you could go. You could divide by 4. So I'm not going to do all these points because, like, for example, 1, that's going to give me a fraction if I try to do 1 divided by 4. So 4 divided by 4 would make that point a 4/1. I'm bringing it down since it's a 1/4. And then 8 would work. That would make it the 0.82. I'm intentionally picking multiples of 4 since that's what I'm dividing by. So on the other side, it would be negative 4/1 and negative 8/2. Now, if you're unsure about these and you're struggling with the little dilation piece, what could you always do? You can always use your calculator still. I'm just trying to teach you tricks to try to help it make it go faster, but if you're struggling with that, use your calculator. It's fine. So if your A value is greater than 1, it makes your graph narrower. It's going to stretch it up. All those values will go up. If it's between 0 and 1, that's going to make your graph wider, so it's going to bring it down like that 1/4 did. And then, as always, use calculator if you need to. Always use that calculator if you need to. Nothing wrong with that. All right, so one more rule to go through, and then we're going to try some practice ones. So this one, the negative is with the x. So this is going to reflect over y-axis. As I said before, if it's with the x, it's over the y-axis. So for example, the point 1,1 becomes the point negative 1,1. And then I got 4,2, so that's going to be negative 4,2. And then 9,3, so negative 9,3. So negative with the x over the y. The other one, the negative is out in front. So it's reflecting over the x. So that means you're going to take everything and bring it down. So 1,1 becomes 1, negative 1. 4,2 becomes 4, negative 2. And then 9, negative 3. And there's our other one, j of x. So there are two rules. If the negative is with the x, reflect over your y-axis. If it's out in front of the whole function, you're going to reflect over the x-axis. So let's take a look at our examples here. So we've got f of x equals the absolute value of x. That's our starting function. And then we've got g of x equals the negative 2 absolute value of x plus 3 minus 4. Describe the transformations in order that occur from f of x to g of x. Well, g of x has that -2, the plus 3, and the -4. Those are the differences between the f of x function and the g of x function. G of x has those three things. So even though it's only three things, there's actually 4 actions that are going to be happening to our equation there. So again, our order is horizontal first. So again, our horizontal shifts would be any numbers that are with x specifically. So in this case, it would be the +3. And that's the one that is opposite of what we think. So +3 means that we move left 3. After horizontals came our reflections, which we will have one because there is a negative sign. We got this negative sign all the way out in the front. So that's going to reflect over the x-axis. If that negative was in the absolute value bars with x, that would have been over the y. But because it's out in front of everything, it's over your x-axis. So next are any stretches. So that's your numbers all the way out in front, which in this case is a 2. So we'll say this is narrower by a factor of 2, because you're multiplying it by 2. And the last one's vertical. So that's our number at the end, -4. Means it's going to go down 4. There we go. So we're going to try it again. So this time we've got f of x equals the square root of x. Now we have g of x equals the square root of 2 minus x plus 5. Describe the transformations in order that occurs from f of x to g of x. I'm actually going to kind of rewrite my g of x here, because then it makes it easier to see the transformations. And I'm going to put my x first underneath that radical sign, so I'm going to make that a negative x because that subtraction sign stays with my x. And then it's +2 plus 5. Well, +5 is outside. So this time this one only has 3. There's no number out in front of the radical sign to make it a stretch or a shrink, so this one's only got 3 changes here. So again, our list, I still have it written up there in green. Horizontal. Is there a number with x? Yes. So there is a horizontal shift. This one's going to be left 2 because it's plus. Plus means left. Then we have reflections, which there is a reflection here. There is a negative sign in front of the x, since it's in front of the x this time. You're going to reflect over the y. As I said, there's no stretches this time. There's no number out in front that you're going to multiply by. And then our vertical +5 means we're going to go up 5. All right, so we got a few just to try on the back. So f of x equals x cubed, h of x equals f of x plus 3 plus 1. What is the value of h of 1? Okay. Well, this one's a little different. We don't have to describe the transformations this time. But what we are doing for our x's is we're going to plug in a 1. So 1 plus 3 makes that actually f of 4. So in order to finish figuring that out, I need to take my 4, and I need to plug it in over here to figure out what f of 4 is. So what is 4 cubed? 64. So f of 4 is 64, so I'm going to plug that in over here. So 64 plus 1 gives us a 65. So number 4, if the quadratic function g of x has a y-intercept of 12, what is the y-intercept for the function h of x, which is 3 times g of x minus 5? G of x minus 5. Well, y-intercept, what is the value of x in a y-intercept? X is a 0 because you're on your y-axis. So your x is a 0 for that. So 3 times g of 0 minus 5, which we already know for the g function, it has a y-intercept of 12. So I can plug that 12 in there. So 3 times 12 is 36 minus 5 gives us a 31. The other way you could have done that is you could have listed out what the transformations were. This one had 2. You got to multiply by 3 to stretch it out to down 5. So essentially that's what we did to the y-intercept, is we took the 12, we multiplied it by the 3, and then we moved it down 5. So we stretched it by 3 and then down 5. All right, 5, we've got the graph of f of x shown below. And then we've got g of x is defined by this formula here. So part A, they want us to graph and label g of x on the axes. So if we look at this, we have 2 transformations that are happening. So you got that plus 3, you got that minus 1. So what are those 2 transformations? What does that plus 3 stand for? Left 3. And then the minus 1 tells us to go down 1. And that's the correct order. Horizontal, remember, comes first. So left, right shifts first. Up, down would be our last ones. So to graph your g of x function, you just have to take each point and you have to move it left 3 and then down 1. So I'll start over here with this one. I'm going to go left 3, down 1, and that's where that new point should be. And then this one, I'm going to go left 3, 1, 2, 3, and then down 1. And then I can connect those 2. And there's that first piece, our straight line piece. So I'm going to go to this piece, 1, 2, 3, down 1. And then I'll connect that. And then this one down over 3, 3, down 1. That's our g of x function. Took the f, moved it 3 to the left, and then down 1. So then they want to know what is the smallest solutions to g of x equals f of x. So g of x equaling f of x, that's just a fancy way of them asking you where do they cross. There's actually two spots where they cross. So the smallest one would be the one more to the left. So that would be at x equals -2. And that's all they're looking for there is the x value when they ask you to solve that. So they want to know if h of x equals our g of x minus 3, explain why the equation h of x and f of x has no solution. Well, it's easiest to explain that if I kind of have my graph drawn on there. So I'm going to move these all down 3. I'll move that down 1 too many. So again, that was taking the g function, so the one we drew, we moved it down 3. So why can't h of x ever equal f of x? Do they cross ever? No. They don't cross each other. So again, they don't cross each other, so no solutions to that. They can't be equal. So 6, we got that parabola right there, 2x. Well, that's not a parabola, that should be a square, that's a typo. 2x squared minus 3x plus 8. Write an equation after a reflection in the x-axis and then a reflection in the y-axis. All right, so reflection in the x-axis, I'll call it g of x, would just simply mean that there is a negative sign out in the front of the whole thing. Now, because we don't leave that negative sign there, we will distribute it so it becomes negative 2x squared plus 3x minus 8. So that would be your new equation after it's reflected in the x-axis. To reflect it in the y-axis, that means the negative needs to be right with the x. So you would actually plug in a negative x. And then we would have to clean it up. So negative x squared turns back into positive, because negative times negative is positive. Negative 3 times negative x becomes a positive 3x. And then your 8 stays as 8. All right, and our last one. Given the function g of x equals 1 over x, write the equation for the vertical asymptote after the transformation to the function j of x. So initially, g of x, the vertical asymptote would be at x equals 0. If you were to graph this, this is what your graph would look like. So it's got that vertical asymptote right there at x equals 0. Can't be 0. So if we look at our new function, we have two transformations that happen to it. You've got the minus 3 and you've got the plus 2. So minus 3 means it moved to the right 3. That's our horizontal shift. We always do that first. Plus 2 means we move up 2. So we're going to do that, and we'll apply it to our vertical asymptote. So if I take 0 and I move it to the right 3, what am I at? 3. And then can I move a vertical asymptote up at all? No, so that part doesn't mean anything to us. Our new vertical asymptote is at x equals 3. All you can do is move it to the right 3.